Hi guys, so in this video we're going to be talking about how to find the area between curves. So let's review first how we found the area under a single curve, and then we'll generalize it to when we have multiple different curves. So taking a look at our graphics here, you guys might recall that how we did this is we began by approximating the area. So likely in your Calculus 1 course, you guys would have started off by taking whatever area you were trying to find and breaking it up into a certain number of rectangles. So looking at this first picture, we have the area of our region exactly, and then we have two different means of approximating it. So the first would be the lower sum, and the second would be the upper sum. How are they different? You notice the heights of the rectangles. If you take the left endpoints with the lower sum, you are underestimating your area. You can see how there's still a little bit of pink above those purple rectangles. And with the upper sum, you're taking the right, and in this case, you would be overestimating the area. You can see how the rectangles are above the curve there. So as you can probably imagine, the actual area of the region is going to be between your lower and upper sum. But let's kind of write down how we went about doing this. So whenever we want to say that we're adding something up, we're going to use this sigma. Okay, that means add up the following. We won't do any exact notation yet. I just kind of want to remind you of the general concept. So we're going to use sigma, and then we're going to add up the area of the rectangle. Okay, and it's going to be a general formula. So as you can tell, each of these rectangles is going to have a different area from the other ones because they're not exactly the same height, but we can generalize a formula. So how we are going to do that is we're going to use the function formula and realize that each of these heights of the rectangle happens to be a point that's on the actual function. Right? So each of the heights of these is a point on our actual f of x. Okay, so let's go ahead and do just one rectangle, and we'll call it the kth rectangle, or the ith rectangle, if you will. So the area of the ith rectangle would be f of one of those little x values. So we'll call the general one in the middle, we'll call it xi. Now notice that as we vary the number of rectangles, this particular example, I have, let's see, 1, 2, 3, 4, 5, 8, 9. There's 9 rectangles there, but you can vary the number of rectangles. So we're going to leave it general. We're using these subscripts that are variable because the number of rectangles could vary. So f of xi is going to give us the height. And for any rectangle, remember that there's length times width. So we've got the height, we need the width. Now notice that when we draw the rectangles, we're making sure that they have a uniform width. Hopefully the picture actually looks like that. But all of these rectangles have a certain width, which can be found by xi minus 1. So that says to find the width, you go and you take the difference of the bigger one minus the smaller one. And a quicker way of summarizing that is just delta x. Okay. And then how do you vary your I? You take your I and you start from 0. That means start with A, your starting point to the end, and then you'll go all the way to the end. So if someone said, break this rectangle up into, break this up into 9 rectangles, you'd have x sub 0, x sub 1, x2, x3, x4, x5, x6, x7, x8. So you go all the way up until n minus 1, where n is your number of rectangles. Okay, so this notation looks super intimidating at first, but let's just talk it through again, kind of familiarize ourselves with it. We won't have to deal with it too much, but I do want all of you to feel comfortable so that if you wanted to read any calculus textbook in the future to refresh yourself, you won't be super intimidated by seeing this because it's going to be everywhere. So this is an approximate of the lower sum. So we have the height of the rectangle, height, or length, if you will, length times width. So that's the area of a general rectangle. And then this is saying add it up from the leftmost rectangle to the rightmost rectangle. So if you computed this, how you would do it is you just compute the area of each one of those rectangles and add them up. This is an approximate. This is not exact. This is going to give you an approximate. Okay, so if anyone is watching this with more of an engineering or science background, you guys will know that approximates are oftentimes good enough. But sometimes you really want the exact. You want the exact area, because we know we're not gonna quite get it with this approximate. So you might think to yourself, how do we take the concept of adding up rectangles and make it exact? Well, I claim that the more rectangles you draw, the more accurate. So what if we just make the width of each rectangle skinnier? Draw more rectangles, so you'll have more total of them, but they're going to be closer and closer and closer. And if we continue to do that infinitely, it's almost like we're taking a limit. So let's see how that works with the area between two curves. Okay, same concept. We see our red curve is the top here and our blue curve is the bottom. And if someone said, okay, we're going to go ahead and find the area between these two curves. It looks a little bit more complicated, but honestly not really that much. All that we're doing is we are slightly shifting the bottom of the rectangles off of the x-axis. So when we go ahead and find the area of the ith rectangle, let's give these curves some names so that we can be on the same page. Let's call the top curve f of x, and let's call the blue curve g of x. Okay, so notice that if we were going to find the height of one of these rectangles, it looks like the top is going to be some point on the f of x curve and the bottom is going to be some point on the g of x. And when you're finding the area, you always want your area to be positive, seeing as areas are positive. So you always want to do top minus bottom. So in this case, we're going to do f of x. Okay, and in general, the area of the ith rectangle means pick any one of these. You would do f of xi minus g of xi. That's going to give you the height. Okay, so that gives you the height. Times, we need to have the width, and that's still going to be a delta x. So this gives us the height times the width. Okay, so hopefully that's straightforward. So that's one area of one rectangle. Now if we want to have an approximate of the total area, we're going to Riemann sum. We're going to take the area for a general, f of xi minus g of xi, all of that times delta x, which we already saw secretly contains xi minus x sub I minus 1. And I'm just kind of condensing it for our ease of writing here, and we're going to index from 0 up until n minus 1, where n is the number of rectangles. Okay, so there's your approximate. Okay, now how are we going to make that exact? What if we let the number of rectangles go to infinity? So I'm going to go ahead and take my sum, my approximate, and I'm going to let n go to infinity. So let's write our sum. I equals 0 to n minus 1. You got my f of xi, g of xi, there's the height, times the width. And I'm going to take the limit of this as n goes to infinity. So what is this going to do? Let's just kind of summarize it here so we have it. As n goes to infinity, the width, aka delta x, goes to 0. Okay, so our rectangles are getting skinnier, and area is then exact. Okay, but as we take a limit, we want to have a better notation than this. This notation's truly terrible, and it really doesn't give us an easy way to write this. So what people did is they went ahead and they took this limit and they gave it a definition. So the way that they summarized what this limiting process was is they came over here, they used this symbol to mean integral, and we'll do the limits here in a second. But as you'll notice, we're finding the area from a to b. So what they would do is they would put the limits. So this is where you start your rectangles, where you stop your rectangles. And then you put your f of x minus g of x. And your delta x going to 0 is represented by saying that you will be integrating with respect to x. So this is where this notation came from. And this is what it means. Okay, so let's highlight this. Okay, so if anyone says, what does the integral mean? This is what the integral means. It was literally defined this way. Okay, and we could have done it with our one curve, but this really shows it along with the picture. So the area between two curves, what do? You take the top minus the bottom, and there it is. Pretty awesome. Okay, so before I move on, I'm going to zoom this out so we can see a little bit better. Okay, so here's our formula for the area of just one rectangle. Here's how we would approximate it with some finite number of rectangles. And to derive your actual exact area, you let your number of rectangles go to infinity, which is going to have the effect of sending this delta x to 0. And you get to your classic integral notation that we know and love. So with this concept, now we have the link between something that is a pain to do because we'd have to sit here and write down the area and compute a limit. We have something that we've learned shortcuts for. We have learned some shortcuts for integration, and we're going to continue to learn shortcuts for integration. So when you guys move forward from here, are you going to be sitting down writing a bunch of Riemann sums? If you have the ability to integrate, no. But if you need to approximate, yes, you very well might need to sit down and write Riemann sums because depending on your functions, there might not be integral shortcuts. So in this course, with me, if you're in one of my classes, I always expect students to have both. I'm always going to ask you for the Riemann sum as well as the integral, right? Because both of them are equally important. Sometimes an approximate will do just fine. Sometimes if an exact answer is possible, then that's even more helpful, obviously. So keep that in mind. I'm going to be asking for Riemann sums in some form if you're in my class. Okay, so let's take a look at an example. So we're going to find the area between the graphs of y equals x squared and y equals 6 minus x. So there we go. So before we go ahead and jump into just setting this up, we'll need to graph these functions. You won't be able to set up the Riemann sum without the graphs. So this is where technology can be super helpful, you guys. In algebra, we went over how to find graphs and intersections very in depth of basic functions, but it's not always going to be the case that your functions are basic like this. So with this example, I'm going to go without the use of technology because it's easy, but there might be some where you really need to use some technology to graph depending on how nasty these curves are. So let's take a look at the first curve. Let's color code that red. X squared, we know it, we love it. It looks like that, parabola. Okay, 6 minus x, let's do that in blue. Y-intercept would be 6, right there, and then okay, so there is our second curve. We've got okay, we need to find the area between the graphs. So it looks like they're going to intersect in two places, and I should kind of extend this graph of the parabola up to where they intersect. There we go. Okay, so now we know, just based on the loose sketch, we're trying to find two intersection points because we need to find the area between them, and let's shade that. We're going to shade that in pink. We're looking for this area here. There we go. Okay, so now visualizing. We need to find the intersection points. This is one of those steps where technology might be helpful. This one, it's definitely not necessary. So we've got setting the two curves equal is going to give us the opportunity to solve for the x coordinates for where the intersections occur. So I've got a quadratic equation, and you might recall how to solve these is you get 0 on one side. Factoring, quadratic formula, honestly either or would work great. X plus 3 and x minus 2 will do this. So my intersections are -3 and 2, and confirming that, yes, that does actually end up working out. Yeah, okay, so that means that this happens at -3, and this happens at 2, which I pretty much had to scale on my rough sketch. So notice that I used algebra to find the intersection points. I didn't rely on just eyeballing the graph. It's very hard to just eyeball intersection points. So if you're using a graphing calculator, you'll need to actually use the find the intersection mode to find those exactly. And it oftentimes, if it's a radical, it's still just approximating the intersection, and your integral is probably going to be a little bit off. And that's just to be expected because your calculator is basically an approximation tool. Okay, so we'll have a lot more on that later as we go through this class about what the calculator can and can't do and what's happening behind the scenes. So now we know where we are slicing our rectangles from and where we are slicing to. We're going from -3 to 2. So when I look at a rectangle, I'm just going to draw one. We don't need to do the whole shebang. If we just go with the midpoint, we can go here to here. The main thing that we want to look at is we are looking at when I find the area of the ith rectangle, I need to know what's the top, what's the bottom. And this picture makes it super clear. The top function is the blue one, 6 minus x. So a general rectangle is going to be 6 minus xi. Okay, this is going to be, let's color code it. Okay, top minus bottom. Okay, and the bottom is the parabola. Okay, this gives me the height. We're not done with the height, and remember we're doing xi because it's a general, one of those general rectangles. So this is the height times the width, which you guys can just use delta x. That's okay. You don't need to use the I notation unless you really like the I notation, in which case you could write this as x sub I minus x sub I minus 1. That would be okay. Okay, so this is the area of just one ith rectangle, and that gives us the ability to go ahead and write our Riemann sum. So our Riemann sum would be adding up from 0 to n minus 1, 6 minus 6 minus x sub I minus x sub I squared times delta x, and then as n goes to infinity, this becomes our integral. And all you need to think of, you don't actually have to compute a limit when you're doing these. I won't ask for that, but what we're doing is as n goes to infinity, delta x goes to 0, and our integral becomes exact. So where are we starting our rectangles? Where are we stopping? We'd be starting our rectangles at the first x value where the area starts, so -3 to 2. Okay, and then remember our i's go away, and this just becomes, you take this part. So it becomes just the height, 6 minus x squared. The delta x approaches 0, and you're just integrating with respect to x. Okay, so that's how that kind of lines up. And we cleaned our formula up. Now we're ready to actually integrate to get what the area is. So the area is going to be what we get when we do the integral. So remember how this works. With these definite integrals, you find the antiderivative and then you evaluate it at the endpoints. So this becomes 6x minus 1/2 x squared minus 1/3 x cubed evaluated 2 to negative 3. And now that we have our basic, what our area will be after integrating, we can go ahead using technology to help you with this part. This is going to be super basic algebra, just plug and chug from here. I'm totally fine with everyone that is in my classes using technology here to assist them doing this part. So once you get your integral set up, you can go ahead and use technology to compute it. I would say that would be the easiest way. So you could use something like Wolfram Alpha. I went ahead and did that here. This is the syntax that would give you the computation, and you'd be getting 125/6. Okay, so obviously on these problems, our focus isn't really on integrating so much as the setup. Now, we are practicing integration techniques in this class. That is something that is important to have in your tool chest, especially if you are more in the closer to math areas of science, especially if you're a mathematician. You need to be very solid with your integration. But unless specified, you are free to use technology to help with this. Here's our problem as a whole, and we can see all the different components. Many people will ask, yes, I could easily ask you for all three of these, the Riemann sum, the integral, the area, so be prepared. Anyway, I will see you guys next time.